So my name is Guillaume, and I will present work on the consequences of the Typhoon 18, which is also known as Mani, and the associated runoff on Lake Biwa. So first of all, now our focus is that usually for water quality monitoring, that's on a time scale of several weeks or months in Lake Biwa, for example. But we are interested in what happens during two monitoring profiles, for example. But these events, okay, so many meteorological events can occur during this day. During this time scale, for example, typhoon or heavy rain, as we are experiencing now. And at this time period, they can affect the transport of particles and material in the lake. And also, these extreme events, distribution over time or their frequency is likely to change according to the IPCC report. So the question we asked is, so how do they impact the transport of materials in the lake? So I'm pretty sure you've seen a lot of these kind of slides about Lake Biwa, but the most important part is that this is the water source, drinking water for 14 million people in the region. And so why Typhoon Mani? I will talk about why Typhoon Mani. So here it is, over Japan. This is satellite images. And so why Typhoon Mani or Typhoon 18 is because, for example, here, due to the very heavy rain, we have a flooding of the rivers around the lake. And also, that was associated with very large wind, which from land-based stations, the wind could reach 15 meters per second at least. And also, due to the heavy rain, and as we saw earlier in the photo, the water was very brown, which is can be seen in the turbidity time series. That the water was so turbid that the record could not be seen. I mean, the values were at the maximum from the sensor. And here, due to the heavy rain, we had a huge discharge at this Ane River right here. The discharge, on average, that's about, say, 5 cubic meters per second. But in this case, there was more than 400 cubic meters per second, which can be qualified as an extreme event. So what's the impact on material transport in the lake? So we also know that the horizontal distribution of particles is not uniform. That's kind of patchy. So we need to know how the particles propagate in water quality purpose. So in the recent publication, for example, we had direct impact from the wind, or also for those we know, the impact of internal waves. But in this case, the wind was qualified as moderate. But in the case of the Typhoon 18, that can be qualified as extreme. And so to do so, we've been using a numerical simulation. So here we have how the bathymetry of the lake. But I will skip a bit all the numbers, but we are using numerical model from Stanford University. And in a numerical simulation, we need to specify how the boundary conditions, for example, the atmospheric boundary conditions, so the wind, for example, that was provided by the Japanese Meteorological Agency with 5 stations, and wind hours. And for the lateral boundaries, so the river's inflow, as we've seen, that was quite enormous. And because we had data from
Can you quickly do, because we
Okay,
don't have time, so.
Okay, so since we had data for only this river, that we had to assume that they were identical for all the rivers that we've simulated, and only one outflow. Yeah, sure. So this was the same photos, the same video that was supposed to be shown at the beginning. And what we saw in the video was this surface temperature distribution during the typhoon. And we've seen upwelling, but I will show figures after that. But in order to make sure that the simulation is doing something consistent with reality, we can use observation monitoring data provided by the Waterworks agency that provides temperature data at several levels within the center of the lake, which are the red dots in the middle of the lake. And we can see that the surface temperature, for example, so 2 meters and 5 meters, are consistent with reality, which is nice, since we are focusing on the surface layer. And so here is just fixed photos. And in order to go further into the consistency check, we can use also MODIS data, so surface temperature, space-bound surface temperature. And on the left-hand side, we have the simulation. So we can see that there are cold water in the northern part of the lake that went up at the surface due to the very strong wind. And also this is visible in the satellite images at 2 timestamps, which increase the confidence into the model. And this animation shows the propagation of particles that were released from the rivers. Since we want to know what's the impact on the propagation of particles due to the typhoon, in this case, that's what we've done. We released artificial particles from the rivers. And so we can see, and also on the right-hand side, this is satellite images of the Lake Biwa after the typhoon. And we can see, for example, some kind of what we call the tiger tail, which is supposed to be surrounded by a blue circle. And we can see in the animation that goes pretty, the particles are released from the rivers, but then they are dispersed quite efficiently. But so just to make sure that the particle release is consistent with reality, we can check again at the same time that if the particle distribution coincides with the observation. So we can see that we have a significant consistency between the two. For example, what we call the tiger tail, and also on the eastern side, that we have an increase of particles concentration. But what was a bit not intuitive is, so on the right-hand side, the big arrows represent the wind direction, but the particles went, so the wind goes southward, but the particles, which was surprising, went up northward, which was not obvious. Okay, so I'm sorry for this, because this animation should show the correlation between the upwelling, so the warm water going back northward and bringing with it the particles at the surface layer in the northern part of the lake, which is in the opposite direction from the wind. But so as quick conclusion, so this is quite a rough sketch of what happened. So we have the wind pushing the warm water and generating what we call an upwelling. But at the same time, there was what we call a runoff, so discharge of particles or turbid water. But then when the wind relaxed or stops, we have an advection of the warm water going back to the north part, and taking along with it the particles. So the implication that in the short term, that the typhoon can make the particle propagation quite counterintuitive, meaning the particles would go northward, whereas the wind goes southward. And so in order to better understand the impact on physical processes, I think that we need to more use of numerical models, since now the numerical models can be consistent with the physics, at least. And using, for example, so in-cast model, or as we are doing in Ritsumeikan, what we call nowcasting system, which is forecasting the state, the physical state of the lake just right now. So what is it now? So thank you for your attention.
Thank you.
Okay.
Floor is open for question. One simple question.
But first of all, I'm sorry for the animation, though.
I think the animation was brilliant. I also miss. I think there is another opportunity. Please show. Yeah, it is very interesting study because they use satellite for the suspended particles and also the comparison of the numerical estimation in very, very high accuracy. And that was in the other side, it's a kind of other application of the satellite image and numerical estimation to predict the river flow into the lake. But the result was very, very detailed. You could see very small river particle coming into the river. So no question, no comment, please.
So there is what we call an upwelling. So you have cold water going in the surface in the northern part, but then when the wind, this upwelling is due to strong wind in this case. So, but when the wind stops, you have the water has to go to a stable state. The water column has to go to a stable state, meaning warm water above cold water. So that's why you have all the water going back to the northern part of the lake and bringing along with it the particles. And when I say counterintuitive, it's because it goes in the opposite direction as the wind.
Okay. Thank you, Dr. Auger. Thank you for your presentation.